this final video of section 2, we come to one of the most important aspects for setting up the coming theory, and that is the notion of orders. Paradoxically, even though this video is very important, I'm going to be a little bit scant on proofs in this section. The reasons are twofold. One is that really the essential information we need here is just to set up some definitions and understand what orders really are. The second is that a number of the statements I'm going to make without proof aren't particularly difficult to prove. Of course, if people get stuck, I'll be happy to make a video, bonus video going through some of those proofs. So to begin, we make a couple definitions. Recall that if we had some relation R which we wanted to be an equivalence relation, we demanded that it be symmetric, meaning that if any two elements, A is related to B, then it should be the case that B is related to A. In this video, we're going to explore sort of two different ways in which we can come up with a sort of opposite notion to this. So we're going to say that a relation R is anti-symmetric if it's the case that A is related to B and B is related to A simultaneously, then this forces A and B to be the same element. So this is one sense in which we could take this to be a sort of opposite property of symmetry, because this says it will never be the case that A is related to B and B is related to A for distinct elements. The second fundamental definition we're going to make here is that we're going to say that a binary relation R is a partial ordering of a set A if, and now three conditions must be satisfied. So like an equivalence relation, we do want this to be reflexive once again. And skipping the second for now, we're going to also demand that the relation be transitive. But now, instead of symmetry in the second position, which we would take for an equivalence relation, we're now going to demand anti-symmetry. So there's three standard examples of partial orders that you should already be familiar with. For example, one could take the real numbers with the partial order, just the regular less than or equal to sign. Now, just one quick note, formally in this course we've not yet constructed the real numbers, we've not described what the set is, we haven't even described infinite sets yet. But I'm just drawing on this example. This is something we'll be able to prove down the road once we actually have built the real numbers into our theory. So it's pretty easy to see that, say, for a real number x, of course x is less than or equal to x. If x is less than or equal to y, and y is less than or equal to x, then of course it must be the case that x is equal to y, so we have anti-symmetry. And certainly the transitivity property holds as well. If x is less than or equal to y, y is less than or equal to z, then we know that x is also less than or equal to z. These are just properties of the real numbers. As another example, for some set A, we could consider the power set of A. And in this case, one can set up the subset, a relation describing subsets. And thus we find that subsets also obey the properties of reflexivity, anti-symmetry, and transitivity. And as one final but important example, consider the natural numbers. And we have the division relation. So in this case, we would say that n is less than m if n were to divide m. And we find that this also obeys reflexivity, anti-symmetry, and transitivity. And just as a little bit of notation, so even though this specific symbol of ordering of real numbers has some pretty specific connotations, in general we will use the symbols this less than or equal to sign, or we might use this sort of curvy one when we want to have talk about two different orders at the same time. So we might even say in the subset situation denote the subset relation by actually using a less than or equal sign. So we're going to use these to describe more general sorts of orders. In order to define the second sort of opposite notion of a symmetric relation, we're going to say that a relation R is asymmetric if it's the case that if A is related to B, then it means that B is not related to A. And there's a corresponding notion of order that goes along with this. We say that a relation R is a strict order if it's the case that the order is asymmetric. So notice in this case we're skipping the reflexive property, but we still are going to preserve the transitive property. So for example here we will use the notation of just the strictly less than sign, or its curvy cousin here. And this notation is suggestive because it turns out that, well, from our previous examples, say taking R now with the strict relation, this is certainly asymmetric. If A is strictly less than B, then it certainly cannot be the case that B is strictly less than A. And it's transitive, which follows more or less from seeing the case with a partial ordering. The same thing could also be said for things such as the strict inclusion of subsets. So one of the lemmas whose proofs I'm going to forego at this point is that, well, we say two things which connects the ideas of a partial ordering to that of a strict ordering. So in general, if I have any ordering R, where by order I mean so partial order, we'll sometimes drop the word partial and simply say just the word order. For any order R, if we define a relation S so that A is S related to B, if and only if A is R related to B and A is not equal to B, then it turns out that S is a strict ordering. Conversely, if S were a strict ordering to begin with, well, you might be able to guess what the case is going to be in this case. If we define a relation R such that A is R related to B, if and only if A is S related to B or A is equal to B, then it turns out that R is a partial ordering. Another essential definition for us is going to be that of comparability. So we say that two elements, A and B, are comparable given some order, so comparable with respect to some order, if it's the case that either A is less than or equal to B, or B is less than or equal to A. Likewise, we'll say that two elements are incomparable if it's the case that A is not equal to B, A is not less than or equal to B, and B is not less than or equal to A. So keep in mind here, when I'm using less than or equal to, I mean in the sense of the order. A and B, these could be arbitrary sets. We're not necessarily talking about numbers here. So just a reminder. So once again, coming to our example of the real numbers under their order relation, certainly every pair of real numbers are comparable with each other. Either x is less than or equal to y, or y is less than or equal to x. We know this must be the case. However, with our natural numbers and the division relation, not all elements are comparable. For example, 2 and 3 are incomparable because 2 does not divide 3, and 3 does not divide 2. Well, and certainly 2 is not equal to 3 in this set. So if it is the case that for all elements of our set, A, A and B are comparable with respect to some order, then we say that the order, or more formally, we like to write the set with the order, we say that this is a linear order, or we also might say that it's a total order. So these two words are interchangeable. Again, we've seen that the real numbers give us an example of a linear or total ordering. Meanwhile, the natural numbers do not give us a total ordering. Another essential definition for us, which will be useful in formulating Zorn's lemma, an equivalent statement to the axiom of choice, is that of a chain. So we say that a subset of a set, subset B of a set A, we say that this is a chain if it's the case that any two elements of B are comparable. So it may be the case that we have a set which is not a linear total order, such as the integers under division, but it could be the case that there may be some subset of it for which all the elements are comparable. For example, if we consider the set of powers of 3, so we consider 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, etc., we know the entire set of integers is not a linear order under the division relation. However, one can see from this set that, in fact, any two elements of this set, one of them will be divisible by the other. Namely, we'll know that 3n divides 3m precisely when it's the case that n is less than or equal to m, where in this case, by less than or equal to, I mean the normal ordering on the natural numbers. And since that itself is a linear total ordering, we know that either n is less than or equal to m, or m is less than or equal to n. So one of these situations must occur. As another example, if we consider the set of elements 1, 2, 3, 4, which again I'd like to highlight, technically in our set theory we haven't defined what numbers are even, so in some sense I'm running in circles, but again we just need something to hold on to for an example. We see that the subset relation is not a total order. For example, the set containing just 2 and the set containing just 3, well, neither of these contain each other. So these are incomparable elements. However, if I were to focus on the subset of the power set, which say contains just the empty set, the set containing 1, and the set containing 1 and 2, you can check by inspection that in fact this is a chain, so that any two members of this set are comparable in the subset relation. On to some more essential definitions. That is the definitions of lower and upper bounds and supremum and infimum, which should be familiar if you've taken a first course in real analysis. As our setup, suppose that we have some partial order on our set A, and suppose we have some subset B of A. We say that X is a least element if X is less than or equal to Y for all Y in B. And we're going to say that X in B is a minimal element if there does not exist a Y in B such that Y is less than or equal to X. These may look like they're saying the same thing, but let's return to our situation with the looking at the collection of subsets on the set containing the elements 1 to 4. So we see in this relation the empty set, this satisfies the property of a least element. Because under the subset relation, the empty set is the least element for this set. And it does also happen to be the case that it is minimal. However, if we were to instead consider the set containing 1, the set containing 2, and the set containing 1 and 2, notice that both the set containing 1 and the set containing 2 are minimal elements. There's no element which is less than these in the subset relation. That is, there are no other sets that are subsets of this in the set that we're focusing on. This is our B. So we actually have two minimal elements. So minimal elements don't have to be unique, but the least elements do have to be unique. And notice what's going on here is that the set containing 1 and the set containing 2, these aren't actually comparable in the subset relation. Therefore, it's implicit in the very definition of a least element that whatever the least element is, it's comparable with all the other elements of B. Now, returning to this definition, if I were to replace the word least with the term greatest, and the word minimal with the word maximal, and then simply swap the roles of these. So instead of having x less than or equal to y, it would be y being less than or equal to x for all y in B. And instead of there not existing a y such that y is less than or equal to b, it would be that there does not exist a y such that x is less than or equal to y. So there's a corresponding definition for maximal elements, and the same thing happens. A greatest element is unique in its position and requires that it be comparable with all the other elements of B. Meanwhile, we can have several different examples of maximal elements. We're going to say that an element x belonging to our set A is an upper bound for our subset B contained in A, if it's the case that for every element y in B, we have that y is less than or equal to x. Now again, this may look very much like the definition we just made of, say, a maximal element of B, but the difference here is that for a maximal element of B, we require that element to lie in B itself. In this case, we're saying that x need only lie in A. And furthermore, there could actually still be other elements larger than x in A if we look at this definition. That is, there could be many upper bounds, some comparable and greater than others, for this relation. Again, it's probably most useful to draw on the example of a set of real numbers. So if we took the half-open interval 0 to 1, we would see that 1 is an upper bound. Well, in fact, it's a maximal element of this set. But let's say we took the open interval 0 to 1 in the real numbers now. Certainly 1 is greater than or equal to anything in this half-open interval. But one could say the same thing of pi, or 2, or 57. All of these numbers in the normal order relation of the real numbers, all of these numbers are larger than every single number in this set. So all of these numbers are upper bounds. Now, the least element of the set of all upper bounds of our set B is called the supremum. In the case of our half-open interval 0 to 1, since 1 we found is in fact an upper bound, it's greater than or equal to everything in the interval from 0 to 1, in this case 1 is the supremum. And it's the greatest element of B since it belongs to the set itself. Now, if instead we were to look at the open interval from 0 to 1, notice that 1 is still the least upper bound. 1 is still an upper bound. It's certainly greater than or equal to everything in this set in the interval from 0 to 1. And there's no smaller upper bound. If one were to take any number alpha that was less than 1, well, either it's less than or equal to 0, in which case it's certainly not an upper bound for this set, or it's at least 0, so that says that alpha lies between 0 and 1, that must mean it lies inside the set from 0 to 1, and, well, if we were to simply take alpha plus 1 divided by 2, this lies between alpha and 1. So alpha could not be an upper bound because we can certainly find a real number that lies between alpha and 1, and so it also belongs to this set. So we find in this case that 1 is still an upper bound, but the thing that's different now is it's actually not a greatest element of the set B because it does not belong to the set B itself. However, it is an upper bound, and in fact it's the smallest upper bound we can find. Thus we call it the supremum. And again, by simply swapping terms, say changing the notion of upper bound to lower bound, well, we say it's a lower bound, again, now instead of if the element x is greater than or equal to every element in the set B, we say that x is less than or equal to every element in the set B. And thus, instead of taking a least element of the set of upper bounds, we're now going to take a greatest element of the set of lower bounds. And in this case, instead of calling it a supremum, we're going to call this a infimum. I've also heard it pronounced infimum, so perhaps someone in the comments can tell me what the correct pronunciation is. Now, we've defined a new sort of structure, that is, a set together with a relation. Often in mathematics, when we give a new structure, it's not really enough to understand the structure itself, the particulars of it, but really, in order to understand what a structure is, we should say when two seemingly distinct structures are the same. That is, we need to define some sort of morphism of structures. Suppose we had two orders, A with its order and a set B together with some curly order relation. Then we're going to say that a function which goes from the set A to the set B is an isomorphism of orders, or we say it's an order isomorphism, if, and, well, there's normally, whenever you see the word isomorphism in mathematics, this means structure-preserving map. And it most often means two things. One is that F is a bijection, and the second is that it preserves the structure of the objects we're looking at. Well, what's the structure here? The structure is the order itself. So, therefore, what the second condition should be is that for x and y belonging to our set A, it should be the case that x is less than or equal to y if and only if f of x is less than f of y. And I should make this last one curly to exemplify that this comparison is happening in B and this comparison is happening in A. Despite my suggestive notation in the previous definition, the orders here do not have to correspond to usual partial orders. They could be strict orders. And the definition goes through just as well, of course replacing the partial orders with strict orders down below. And in this case, we actually find that the second condition on an isomorphism is a bit overpowered for the case of strict orders. What I mean by this is the following theorem. If I have sets A and B, which are linearly ordered sets, meaning they each come with their own order, and in this case we're assuming that order to be strict, and if we do have a bijective function between the sets, such that x less than y implies h of x less than h of y for all x and y in A, then it's the case that H is an isomorphism. So what we're saying is that it's enough to have one direction and not necessarily the other. Of course, in order to prove this, we have to begin with two arbitrary elements of A, x and y, and we're supposing that it is the case that h of x is strictly less than h of y. We're going to proceed by contradiction here. So what we want to show is that x is less than y. And so let's suppose the case that this doesn't happen. Well, there's two possibilities. Since these sets are linearly ordered, all the elements must be comparable. So it's either the case that the elements were equal to begin with, in which case h of x has to be the same thing as h of y, and, well, we've already got a contradiction because we're assuming h of x is strictly less than h of y. Or it's the case that y is strictly less than x. But by assumption, we're assuming that h preserves the order relation in the forwards direction. That is, this implies that h of y is strictly less than h of x in B. But again, this contradicts our assumption that h of x is strictly less than h of y. Therefore, we find it must be the case that our assumption that x was not strictly less than y to be erroneous. That is, x is less than y, and the theorem is proved. So that does it for this video. Next time, we'll finally get to the construction of infinite sets and natural numbers. As always, your comments, questions, and concerns are greatly appreciated, and I'll see you next time.